Hello, geometry students. Welcome to this video on geometric probability. So we're going to work through a few examples that show some geometry with respect to probability. So let's take a look at example number 1 that says point X is chosen at random on segment JM. Find the probability that X is on KL, segment KL. So let's give this some context. So let's say we had a bug. This kind of looks like an alien bug. But let's say a bug was flying around, and if the bug is going to land on segment JM, what is the probability that it lands on KL? All right, so if you look at this entire segment, its measure is 14. So from J to M is 14. So what is the probability that our bug is going to land on this segment from K to L? Well, that would just be 7 out of 14, which reduces to 1/2. All right, how about this example? This example that says, what is the probability that X is going to land on LM? So what if the bug takes off and he flies around, he's going to land on segment JM. What is the probability that he'll land, boom, right here on JM? So let me highlight that a different color. Let's make it green. So what is the probability that he's going to land in the green part of segment JM? So that would be a probability of 4 out of 14, which reduces to 2/7. All right, and then one more. Suppose our bug, let me erase a little bit. Let me, erase these markings. Suppose our bug takes off again and he starts flying around. What is the probability that he's going to land on segment KM? So that would be this part of the segment from here to here. So what is the probability that he's going to land on that yellow part of segment JM? That would be 11 out of 14, which doesn't reduce any. Now let's take a look at example number 2 that says 4 birds are sitting on a telephone wire. What is the probability that a 5th bird landing at a randomly selected point between birds 1 and 4 will sit at some point between 3 and 4? So here we have these birds sitting on a wire. The distance from the first bird to the last bird is a total of 24. So if we have a bird flying around, what is the probability, and he comes and lands on that wire somewhere between the first and the 4th bird, what is the probability that he's going to land between birds 3 and 4? That would be this area right here. So here comes a bird. He's flying around, flying. He's going to land somewhere on this wire between birds 1 and 4. What is the probability that he lands right here between birds 3 and 4? That would be the ratio of 8, which is the distance between birds 3 and 4, to 24, which is the total distance between all 4 birds. And of course, that reduces to 1/3. All right, example number 3 says, use the information at the left. Well, that information says that a DART train arrives or departs a station like Cedar on the red line every 4 minutes. So assuming that you arrive at Cedar on the red line at a random time, what is the probability that you will have to wait 3 or more minutes for a train? So why don't we turn this into something where we can use geometry? So let's draw a line segment. And on that line segment, our line segment is going to represent wait time, how long you have to wait for a train to come in. So this would represent 0, and then 1 minute, 2 minutes, 3 minutes, and then 4 minutes. So got my line a little bit too long. All right, so on this timeline, if you were going to arrive, the question is, what is the probability that you will have to wait 3 or more minutes for a train? Well, that would be on our timeline, that would be this portion of the timeline from 3 to 4 minutes. So I think you can see geometrically that the probability of you having to wait more than 3 minutes, this yellow portion is 1/4 of the whole timeline. So your probability of having to wait 3 or more minutes would be 1/4. And then let's move on to example number 4, which says, Julio is watching a television and sees an ad for a video game that he knows his friend wants for her birthday. If the ad replays at a random time in each 3-hour interval, what is the probability that he will see the ad again during his favorite 30-minute sitcom the next day? So let's take this 3-hour block of time and let's turn it into a timeline. And then we're going to break that timeline into 30-minute intervals. So we have from 0 to 30, and then 30 to 60, and then to 90, to 120, 150, and then 180 minutes is a total of 3 hours. So now his show that he wants to watch, his favorite sitcom, is 30 minutes. So let's just pick a 30-minute block. Let's say that the sitcom comes on from 60 minutes to 90 minutes in that 180-minute interval. So what is the probability that the ad will show up during this 60 to 90-minute block, or this 30-minute block from 60 minutes to 90 minutes during this 180 minutes? Well, that would be the probability of 30 minutes out of 180, and of course that reduces to 1/6. So the probability that he's going to see the ad during his 30 minutes show is 1/6. Example 6 says the following. It says, suppose a skydiver must land on a target of 3 concentric circles. If the diameter of the center circle is 2 yards and the circles are spaced 1 yard apart, what is the probability that the skydiver will land in the red circle? So let's draw a picture of this. So we have 3 concentric circles. So we have our inner circle and then 2 more circles, and those circles are spaced 1 yard apart. Now notice it says that the diameter of the center circle is 2 yards. Well, if the diameter of the center circle is 2 yards, that means that the radius, oops, I meant to do that with a pen. That means that the radius of that center circle is 1, all right? And then the radius, each circle is 1 yard apart. So the radius of the big circle then would be 3 yards, all right? So now, what is the probability that if the skydiver is going to land in this circle, what is the probability that he's going to land in the red part? Well, we're just going to take the ratio of the area of this red circle, that's this part. Let me highlight that for us. That would be this part, okay? We're going to take the ratio of the red part to the ratio of the entire circle, all right? So let's just write a ratio. So the area of the red circle then would be pi times its radius squared, so that's going to be pi times 1 yard squared, and then to the ratio, that ratio of the area of the red circle to the area of the whole circle would be pi times 3 squared. Remember, the radius of the entire circle is 1 plus 1 plus 1. That would be a radius of 3. So now we can reduce this fraction a little bit. We can get rid of the pi's, and then 1 squared over 3 squared, we can simplify that, is equal to 1/9. So the probability that if the skydiver is going to land in this circle, the probability of him landing in the red part is 1 out of 9. All right, before we do example 6, since your notes aren't in color, why don't we take a minute to identify everything. This sector of a circle with a 44-degree central angle, that's the yellow sector, so go ahead and label that yellow. This looks pink to me. It's kind of pink or magenta. This portion, this sector is blue, this sector is red, and this sector is green. So go ahead and take a minute to label that, because if you look at your notes later without looking at this video, your notes aren't in color, so that's going to help. All right, so here's what example 6 says. It says, use the spinner to find each probability. If the spinner lands on a line, that it is spun again. So we don't count the spinner landing on a line. So it's gonna, anything we count is when the spinner lands in one of these colored areas. Okay, so the first probability says, what is the probability that the pointer lands on the yellow? Well, this yellow sector has a central angle of 44 degrees, and that would be 44 out of 360. So our first answer then is simply 44 out of 360. You can leave it like that if you want, Or we could reduce that to, there's a common factor of 4, so we could reduce that to 11 over 90. Or we could even write that as a percent. It would be 12.2% if you wanted to write it as a percent. All right, and then the second probability says, what's the probability that the pointer lands on blue? Well, this blue sector has a central angle of 84 degrees, so that probability would be 84 out of 360, which reduces to 7 out of 30, or that would be approximately, I guess I should put a squiggly equal sign, that's approximately 23.3%, all right? And then look at the next one that says, what is the probability of the pointer not landing on green? Well, green is 110 degrees out of 360, so the probability of not landing on the green, 360 minus 120, 360 minus 110 would be 250. So that would be, let me put this answer right here, that would be 250 out of 360, which reduces to 25 out of 36. Or if you wanted to write that as a percent, that would be approximately 69.4%. All right. And then the next one, what is the probability that the pointer lands on red? Well, red is 92% 92 degrees out of 360 degrees. So sorry, I should have spread out these examples a little bit more. So let's go ahead and put this answer over here. So that would be, what did we say, 92 out of 360. Which reduces to, let's see, 23 out of 90, or if you want to write that as a percent, it would be 25.6%. And then last but not least, let's look at this last one, the pointer landing on neither red nor yellow, all right? So red and yellow together, that's 44 plus 92. Let's see, let's write this out. So 44 plus 92 is 136, and then 360 minus 136 is 224. So the probability of the pointer landing on neither red nor yellow is 224 out of 360. That reduces to 28 over 45, or that would be approximately 67.2%. All right, so let's let me mark all these answers so we can see them. And the last one. All right, in these next examples, you're definitely going to see some geometry at work. The directions say, find the probability that a point chosen at random lies in the shaded region. Assume that the figures that seem to be regular and congruent are actually regular and congruent. All right, so the first thing you're going to need to do, because the copies didn't come out very clear, is take a minute and go ahead and shade in these boxes. It didn't copy very well, so if you could shade in those boxes. So if we are finding, remember the directions say to find the probability that the point chosen at random lies in the shaded region, what is the probability that if a bug flew around and he's going to land in one of these squares, he lands in one of the shaded ones? Well, this one, if we just count the squares, there are 16 squares. 1, 2, 3, 4, 5, 6 of those are shaded. So the probability of choosing a point that lies in the shaded area would be 6 out of 16, which reduces to 3/8. Or if you prefer, you could write that as a decimal, which would be 0.375, or if you prefer, you could write that as a percent, 37.5%. So any of those answers is acceptable because they all represent the probability of a point chosen randomly in this region lands in the shaded part. Okay, on example 8, Likewise, you might want to shade in this part that you can see is yellow on the video, but it didn't copy very well on your copy of the notes. So shade that in, and then let's find the probability of a point chosen at random actually lands in this shaded area. Well, we're going to have to write a ratio, and we're going to take the ratio of the shaded area to the ratio of the entire circle. So if I want to get the area that's shaded, to get the shaded area, I'm going to have to take the area of the entire circle and subtract the areas of the two white triangles. So the area of the entire circle minus the area of this big triangle minus the area of this little triangle. That would be the area of the shaded region, and then we'll put that over the area of the whole circle to find the probability. So let's go ahead and find the area of the shaded region. So that would be pi times the radius squared. Now this 5 refers to the entire diameter. So if that's the diameter, then the radius would be 2.5. All right, so that's going to be pi times 2.5 squared is the radius of the circle minus the area of this first white triangle. Well, if this is a diameter, that means that we have an inscribed angle that's intercepting a semicircle. So you'll recall from our previous work that this is a right angle, so it has to be an isosceles triangle. So this measure is also 4. So to find the area of this white triangle, we'll take 1/2 its base times its height. So that's going to be 1/2 4 times 4. All right, and then we also have to subtract the area of the other little triangle. Well, you'll notice that this triangle, the two sides of the triangle are radii of the circle. So we know that they are congruent, and we know from what we said earlier that these radii are 2.5, and if it's an isosceles triangle, it has to be a right triangle. So to find the area of that little triangle, it's going to be 1/2 its base times its height. All right, and so what we've written right now is an expression, or we've written the arithmetic that we would do to find the area of the shaded region. So to get the probability that a point that is chosen randomly lands in the shaded area, we need to take the area of the shaded region over the area of the entire circle, which is pi times 2.5 squared. So I think you'll agree with me, this is a good time to grab a calculator, and when you do, this is approximately equal to 0.443, or if you prefer, we could write that in percent form, which would be 44.3% approximately. Okay, and then last but not least, let's find the area or the probability of a point chosen at random in this rectangle is going to be in the shaded part. So remember, the direction said assume that shapes that appear to be congruent really are congruent. So these are all congruent circles. So to find the area of the shaded part, we'll find the area of the rectangle, and then we'll subtract the areas of 6 circles, all right? So to find the area of that rectangle, let's figure out its dimensions, its length and its width. Well, if these circles all have a radius of 3, so here's a radius of 3, here's a radius of 3, and then another radius of 3, and I mean 2 more radii and 2 more radii that have a 3. So that means from here to here would be 6, and there's 3 of those. So the length of our rectangle is 18, and by the same reasoning, the height of our rectangle is going to be 12, because there would be a diameter of 6 here and a diameter of 6 here. All right, so to get the area of the shaded region, we'll take the area of the rectangle, which is 18 times 12, minus the area of 6 circles. So 6 times the area of one of those circles, well, the area of just one circle would be pi times its radius squared, pi times 3 squared. All right, so what we have just written is the arithmetic we would do to find the area of the shaded part, and then we need to put that area over the area of the entire rectangle, so that would be 18 times 12. All right, and then I would use a calculator on this one as well. That probability in decimal form turns out to be about 0.21, or if we were going to write that in percent form, it would be 21%. All right, so if you have any questions, be sure and ask me in class, and you can. And and I will see you then.